The ergosphere is a region located outside a rotating black hole. Its name is derived from the Greek word ergon, which means work. It received this name because it is theoretically possible to extract energy and mass from the black hole in this region. The ergosphere has an oblate spheroidal shape that touches the event horizon at the poles of a rotating black hole and extends to a greater radius at the equator. The equatorial maximum radius of an ergosphere corresponds to the Schwarzschild radius of a non-rotating black hole. The polar minimum radius can be as little as half the Schwarzschild radius if the black hole is rotating maximally. Within the ergosphere, space-time is dragged along in the direction of the rotation of the black hole at a speed greater than the local speed of light in relation to the rest of the universe. This process is known as the lens-Thiing effect or frame dragging. Because of this dragging effect, objects within the ergosphere could not be stationary with respect to the rest of the universe unless they were to travel faster than the speed of light with respect to local spacetime. A suspended plum, held stationary outside the ergosphere, will experience infinite/diverging radial pull as it approaches the static limit. At some point it will start to fall, resulting in gravitomagnetically induced spinward motion. Another result of this dragging of space is the existence of negative energies within the ergosphere. The outer surface of the ergosphere is called the static surface. At the static surface, a particle moving against the flow of space at the speed of light is static relative to a distant observer. This is because the space here is being dragged at exactly the speed of light relative to the rest of space. Outside this surface, space is still dragged, but at a rate lesser than the speed of light. Since the ergosphere is outside the event horizon, it is still possible for objects to escape from the gravitational pull of the black hole. An object can gain energy by entering the black hole's rotation and then escaping from it, thus taking some of the black hole's energy with it. This process of removing energy from a rotating black hole was proposed by the mathematician Roger Penrose in 1969, and is called the Penrose process. The theoretical maximum of possible energy extraction is 29% of the total energy of a rotating black hole. When this energy is removed, the black hole loses its spin, and the ergosphere no longer exists. This process is considered a possible explanation for a source of energy of such energetic phenomena as gamma ray bursts. Results from computer models show that the Penrose process is capable of producing the high-energy particles that are observed being emitted from quasars and other active galactic nuclei. The size of the ergosphere, the distance between the ergo surface and the event horizon, is not necessarily proportional to the radius of the event horizon, but rather to the black hole's gravity and angular momentum. A point at the poles does not move, and hence has no angular momentum, while at the equator the distance covered by a point in the black hole within a given time is greater than any other point at the black hole, which gives it the greatest angular momentum. This difference of angular momentum that extends from the poles to the equator and is reflected over the equator is what gives the ergosphere its oblated shape. If the gravity or the rotation speed increases, the size of the ergosphere increases as well. Conversely, if the rotation speed decreases, the size of ergosphere decreases, too.